Sections 2.6 and 2.7 deal with composite functions in 2.6. We've done a little bit of that already. We just didn't name it that. And in 2.7, we're going to do something called inverse functions. Here's your homework for 2.6 and for 2.7. These right here, 25 through 28, focus on these. The algebra involved in solving and checking your work on these. There will be a lot of that in this video toward the end, and this is what you can expect to see on a test. Just the algebra part of it is great practice. So it's going to be super stressed. Okay, topic 1, composite functions. A composite function is when you have a function and you're going to cram the other function in for the x's, okay? It's one function inside another, right? So previously, when you did f of x plus h, you were finding a composite function. You had f of x, and then you had g of x, which was defined as x plus h, and you found f of g of x, okay? You took this function and plugged it in for the x's in this function, and that gave you this. So you've been there and you've done that a little bit. In that same section, you were given a function and you were asked to find something like that. Well, that's a composite function, all right? The g of x would be defined as x minus 3, the thing that you're cramming in. So you've already done this stuff, so it should just be mostly review. I want you to do this in the same way that I told you to do it before. You're going to take the outside function and copy with just parentheses where you see x's, and then you'll go back and fill in the parentheses. But you copy the structure of one, and then you plug in the other. Now, notation. In your book, you'll see this little open circle, and that represents of, okay? F of g of x is the way you read this. But to me, it makes more sense to write it this way. Normally you have f of x, but instead of plugging in an x, we're plugging in the function g of x. Now, with this notation, it's obvious which function is the outside function. This is the boss. This is the guy that gets, this is your input, okay? So you're going to take that f function, which is x squared minus 4x, and you're going to copy the structure of it, but then you're going to go back and plug in the function g of x, the whole thing, and then you simplify that. So we have 2x minus 3 times itself. Don't just square the bits. Distribute the minus 4 with the minus with the 4. I'm sorry, stumbled a bit. And 4x squared minus 2 times 3 is minus 6, and we get that twice, plus 9. Combine like terms, and we get 4x squared minus 12 minus 8x is plus 9 plus 12 plus 5 is going to give me 26, I think. But the point is, when you find a composite function, you plug one function into another function, you get a brand new function. Now, let's go the other way. In the next problem, we have g on the outside, and we're plugging f of x in. So we start with that outside function, and we copy that structure. It's 2 something minus 3. And the something is the entire function f of x. This one's much easier. So you distribute that 2 and combine like terms, and you get a brand new function. So that's all that composite functions are. You're just taking one function as your outside, copy the structure, and then cram the inside function into those parentheses and make sure you simplify. If you don't simplify it all the way down, then you haven't worked the problem. Okay, some more examples. Here we have f on the outside. F is defined as this, and we're going to cram the g, which is defined as this, into the f. So f says 4 minus something squared. The something is that, x minus 3 times itself. Notice that we're subtracting, so I'm going to keep the parentheses. X squared minus 3x twice, positive 9, and then distribute the minus sign. Combine like terms, I get negative x squared, positive 6x, negative 5, and there's my new function. Now g of x says something minus 3. The something is the f of x. Combine like terms, and you get a new function. Okay, the next one is a little bit more difficult, but these are the ones that you need to make sure that you can do, all right? The first thing you're going to do is copy the structure of the outside. That means these two x's are going to be parentheses. And then copy the inside function, which is this whole thing, into those two sets of parentheses. So the outside function is a fraction with something plus 1 over something minus 3. And the something is the entire function g of x. Now, one mistake that I see a lot is that students will put the top in the top and the bottom in the bottom, and that's not what this says. It says the entire function g of x and for each of those things. So this has to be the entire function. All right, now, if you don't simplify it, you haven't finished the problem. So the way to simplify these things is to get rid of the fractions that are inside the fraction. And we know how to cancel denominators because we've done it plenty of times. So we're going to multiply the top and the bottom by the common denominator. What does this equal? It equals 1. So we haven't changed the value of anything. But just like when we were doing equations with fractions in them, this guy right here gets distributed to both pieces. Okay? I'm going to write that down once, and then I'm not going to write it down again. So we're going to have 2x minus 4 over 3x plus 5 being multiplied by 3x plus 5, which is over 1. Then I have plus 1, which is being multiplied by 3x plus 5. All I did is distribute. Do the same thing on the bottom. 2x minus 4 over 3x plus 5 multiplied by 3x plus 5. Then we have minus 3 times 3x plus 5. Now, what's going to happen? Exactly what we wanted. The bottom is gone. The bottom is gone. Now, we've eliminated any fractions inside of our fractions, and we're left with the top plus 1 times the bottom over the top minus 3 times the bottom. Now you've got to distribute the minus with the 3 on the bottom. Move that up a little. I'm going to do that in blue. This is going to be 2x minus 4 minus 9x minus 15. All I have to do now is combine like terms. On the top, I have 2x's and 3x's, minus 4 plus 5. On the bottom, 2x minus 9x, minus 4 minus 15, and we get that. And that is our new composite function. All right, let's do another. We have the outside function is f, and f says 3 something plus 2 over something minus 1. And the thing that gets plugged into the parentheses is the entire g of x function, x plus 2 over x minus 3. Then we're going to multiply the top and the bottom by the denominator, but then that gets distributed. When we multiply the top and the bottom by the same thing, we're just multiplying by 1. So, bang, 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 we get 3 times the top, it's always this form, plus 2 times the thing that was in the bottom. On the bottom, we have the top minus 1 times the thing that was on the bottom, distribute, plus 2x minus 6 over x plus 2. Distribute that minus sign, don't mess that up. You get a plus 3. Combine like terms. Notice we get 6 minus 6. So I have 5x on the top, and now the x's cancel on the bottom. And look what happened. Bang, bang, I get equals x. All right, let's do it the other way. Now g is on the outside, and g says something plus 2 over something minus 3, and we plug in the f. Multiply everybody by the denominator. X minus 1, x minus 1. It gets distributed, right? So all we're doing is multiplying the top and the bottom by the same thing, and then using the distributive property. Bang, 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 bang. I get the top plus 2 times the bottom. Whoops, minus 1. The top minus 3 bottoms. And this is going to give me 3x plus 2 plus 2x minus 2 over 3x plus 2 minus 3x plus 3. And I get 5x over 5, which equals x. Okay. This is very interesting because I got an x when I plugged g into f, and I got an x when I plugged f into g. There's a very special relationship between these two functions, and what it is an inverse relationship. This process will undo this process, and this process goes backwards with this process. So there's a very special relationship between these two. I said that already. Let's examine that relationship more. Now we're in 2.7 inverse functions. Now, if you plug one function into another and you get x as your answer, and you can do it the other way and you get x as your answer, then these two functions are inverses of each other. And we write inverse with a superscript. This would be read g inverse of x. And this is just showing that f and g are each other's inverses. And this is the way you need to remember it. The f of its inverse is this equal to f inverse of f, and they both equal x. That's the special relationship. And now let's think about what that means practically. Okay, in this example, we have f of x equals this, and f inverse, excuse me, I forgot my little -1 here. F inverse equals this. Now, what that means is if I take this function and plug it into that, I'm going to get an x back because the input into the input is going to give us the input. I know, right? So f says 3 times it plus 2, and the thing we're plugging in is its inverse, and you can see what happens. The 3 and the 3 cancel. I get x minus 2 plus 2, and the minus 2 and the plus 2 cancel, and I get equals plain old x. And if you do it the other way around, you're going to get the same thing. If I plug all of this in here, the plus 2 minus 2 goes away. I'll get 3x divided by 3. It's just x. Now, look at this graph. This is each of these functions graphed on the same coordinate system. So this guy right here crosses at 2, and rise over run is 3 over 1. So it's a slope of 3, and you see that graph. If I graph this thing, I'm crossing at -2/3, and my slope is 1 over 3. So from -2/3, I'm going to go up 1 over 3. Okay? This red line is the line where x and y equal each other. Now think about what would happen if I take this axis and I flip the entire coordinate system on the line where the x's and the y's are equal. Then the green line goes up here and the blue line goes down here. And I get the exact same picture. They've just traded places. Now, that's a clue for what you have to do when you're finding an inverse function. The x and y's trade places, okay? So that's going to be your process. You have to recognize that f of x is just y. And if y equals 3x plus 2, let me do this in a different color here. If y equals 3x plus 2, then I'm going to change the x and the y around. And then I solve for y. And that is the inverse function. And that's the process that you're going to follow to solve for the inverse. Okay, another example. These functions right here, we're going to get to these, I think it's chapter 4. But what this is called the natural number. This is e. It's 2.71 ... It's kind of like pi. It never repeats. It never stops. It's called the natural number. Notice that x is the exponent here. So these values are my exponents. Now I can take a number and raise it to any power that I want. So the domain of this problem is all real numbers, right? Any x can be plugged in there. But if I have a positive number and I raise it to a power, then that's never 0 and it's never negative. So if x is 0, y is the e to the 0 is always 1. Anything to the 0 power is 1. So I get this curve right here, and we'll talk about that more when we get to it a little bit later. This guy right here is called the natural logarithm, and it asks what exponent will make e equal this. So if I rewrote that in an inverse kind of way, y equals the ln of x means that e, the log equals the exponent. That's the relationship. And you can see how these two guys are inverses of each other because this y equals the ln of x means e to the y equals x, and you see how this guy right here is y equals e to the x. Do you see how we just switched the x and the y in those two functions? And look at the graph. This is the line where x and y are equal to each other, and you see the e to the x looks like this, and if I flip it on that line, I get that. Here, the negative x-axis is an asymptote. We'll talk about asymptotes in Chapter 3. And here, the negative y is the asymptote. Here, I'm crossing at y equals 1. Here, I'm crossing at x equals 1. So you can see the picture. It's not perfect, but if you flipped it, they would change places. And that's what an inverse function looks like. Now, another thing, let me just write this down really quickly. F of x says e to the something, and the inverse is the ln, and those processes will undo each other. F inverse says the ln of something, and the thing I'm plugging in is f of x, and both of those guys give you back the x. More on that to come in a future chapter. Okay, before we work this problem, I want to state something very plainly here. For an inverse to exist, for an inverse of f of x to exist, f of x, not only is it a function, it must be a one-to-one function. We talked about that in a previous video. What does that mean? Every x has only one y, but every y has only one x. And to demonstrate that, if I have f of x equals x squared, that looks like this, right? And if I take that function and flip it on the line, I get that. And that isn't a function. Look at this, x has two y values, not a function. So I can't find the inverse of f of x. And we can see that. Look at the black graph. I can see that it's not one-to-one because for this y value, I have two x values. See that? So if it's not a one-to-one function, there is no inverse, okay? Now, if I take that same function and I limit my domain of this to only be positive values of x, that would only give me this half. And when I invert that, I get the actual graph of the square root of x, positive square root of x. So in that case, I could find an inverse. But in general, if it's an even power, it's not going to have an inverse because it's not a one-to-one function. Okay? Now, let's work this problem. My process is to switch the x and the y. First off, you have to recognize that f of x is y, right? So the step number one is to switch the x for the y. Step number two, solve for y. So I get x minus 5 equals 2y, and y equals x minus 5 over 2. And that is the inverse of the function I started with. Now, look at this. This is just a line. All linear functions are one-to-one. So we can find that function, that inverse, and the inverse itself is a function. And that's how you do it. How do you check it? You plug one into the other. And that's easy to do, so I'll let you do that. Okay, this one is a little bit more challenging, and that's okay. We have y equals x plus 1 over x minus 4, and I'm going to switch the x for the y. And I'm going to solve for y. That's the process, okay? So, while you're working these problems, and these are the kind that you're going to see on the test, I said that. I said this is the kind you're going to see on the test. You need to write it down. What's the issue that I have here? If I'm solving for y, keep reminding yourself as you go through the process, the whole point of it is to solve for y. So what makes it difficult to solve for y? Well, first off, I have y in my denominator. How do I get rid of that fraction? I multiply both sides of the equal sign by the denominator. That's going to give me x times y minus 4 equals y plus 1. Go back to what you're planning to do. Solve for y. What makes it difficult to solve for y? I've got y inside the parentheses. How do you get rid of parentheses? You multiply through. It won't do me any good to divide the x over here because then I'll have a y in a fraction again. Okay? So let's distribute the x. Now what's wrong? Why can't I just easily solve for y? Well, I got a y over here and a y over here. I got to get both of my y's on the same side of the equal sign. So I'm going to take this guy and subtract him over here, but I don't like this guy being there. I'm trying to get y by itself. So I'm going to move him to the other side. So that's going to give me xy. I'm going to subtract y from both sides. And then I'm going to add the 4x to both sides. What am I supposed to be doing? I'm supposed to be solving for y. Well, I got my y's together on the left-hand side, but I can't add these two y's because they're not like terms. I have an x there. So the only way to get just a plain old y is to factor it out on that side. The process is always going to be the same for these problems. Factor out the y. And now you see all I have to do to get y equals is to divide away the crap I don't want. I had that over on the left, and I'm dividing away that. Guess what I have? F inverse equals 4x plus 1 over x minus 1. Now, you're not done because the next thing you have to do is to check your answer. How do you do that? You're going to plug the inverse into the function and make sure that that equals x. Okay? So, f of x says fraction something plus 1 over something minus 4. We've been here and done that. And the thing that gets plugged into the parentheses is the entire inverse function. So it's a fraction, 4x plus 1 over x minus 1. Fraction, 4x plus 1 over x minus 1. What do I do now? I multiply the top and the bottom by the denominator, but it gets distributed. We've done this. And now bang, 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 bang. What's left? The top plus 1 times the bottom over the top minus 4 times the bottom. I'm going to distribute on the top, or I'm sorry, combine like terms on the top. 4x plus x is 5x, plus 1 minus 1 goes away. I bet I'm going to get a 5 on the bottom. Let's check it. This is 4x plus 1 minus 4 times x minus 4 times minus 1 is plus 4. The 4x's subtract away, and I get a 5 on the bottom. Bang, bang, and I'm left with x. And it checks out. But I'm going to do it again. I'm going to find f inverse of f of x, just to be sure. F inverse says 4 times something plus 1 over something minus 1. And the something is the entire function itself. X plus 1 over x minus 4. Multiply the top and the bottom by x minus 4. It gets distributed everywhere. Always the same process, guys. Bang, 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 bang. What am I left with? 4 times the top plus 1 times the bottom. The top minus 1 times the bottom. Distribute everywhere. 4x plus 4 plus x minus 4. The 4's go away. I get 5x. On the bottom, x plus 1 minus x plus 4. Got to distribute the minus sign. The x's subtract away. 1 plus 4 equals x. So that's the process that you're going to have to do. And this is the kind of problem you're going to see on the test. Okay? One more of these. Find the inverse function. F of x is just y, right? I'm going to now switch the x with the y's. 4y plus 1 over 3y plus 2. Multiply away the denominator. Distribute the x. Be careful. And now I want to get my y's together. So I'm going to subtract, sorry, that's a y. Subtract 4y from both sides. And I also want to get rid of the 2 x's. What does that leave me with? Notice that these are not like terms. I can't add them. I have to just write them down. 3xy minus 4y equals, notice that I can't combine the minus 2x and the positive 4. What's next? I want to solve for y, right? So I have to factor it out. 3x minus 4 minus 2x plus 1, and then I divide away the stuff I don't want. Minus 2x plus 1 divided by 3x minus 4. Now you might have moved things around in a different way and gotten that. It's the same thing, okay? So I say that f inverse of x equals minus 2x plus 1 over 3x minus 4. And now I have to check it. Find f of f inverse. F says fraction 4 something plus 1 over 3 something plus 2. And I'm going to plug the inverse function in. Negative 2x plus 1 over 3x minus 4. Negative 2x plus 1 over 3x minus 4. Multiply everybody by the denominator. I get 4 times the top plus 1 times the bottom. On the bottom, I get 3 times the top plus 2 times the bottom. That gives me minus 8x plus 4 plus 3x minus 4. So that looks good. My numbers go away. I'm going to end up with negative 5x on the top. I bet I'm going to end up with negative 5 on the bottom. The x's will cancel and the constants will add to negative 5. Let's see. 3 times negative 2 gives me negative 6x plus 3. Now distribute the 2 plus 6x, perfect, minus 8. That gives me negative 5x on the top. The 6x's cancel, and I get negative 5 on the bottom. Booyah. And I'll leave it to you to plug things in the other way, find F inverse of F. That's it, guys. That's the end of this chapter. Enjoy your homework.